Okay, so the second part in this module on data distribution is continuing with the description of your data distribution, and now it's going to be numbers that are a variety of numbers and summary statistics that you can use to not only describe the very basic mean and variability, but the shape of your distribution. Okay, so the third and fourth moment. If you don't remember, go back to the previous video where we calculated or we showed that the first and second moment are related to the mean, or it's zero deviation from the mean, but it's related to the mean. And the second is your variance, or related to your standard deviation. Okay, and the first and fourth moment here, I won't need you to recognize or to be able to use the formula. I just show them here, this formula and this one, to make a point I hinted at before, which is the fact that these formulas are a progression, okay, on the same pattern. And if you remember, for the first moment, we had the sum of the differences between each sample and the mean, okay, divided by n. The second moment, we had the sum of the difference squared divided by n minus 1. Here we have the sum of the differences cubed, so power 3, divided by n minus 1 and minus 2. So it starts to be a little bit more complicated, but you see the same pattern of the sum of the difference squared, cubed, here to the power 4. Okay, obviously this moment there's a lot more going on, but it's the core of it relies partly on the same thing, right? This summed difference to a certain power. Okay, now beside making that point that you have a pattern, and that's why using the term moment really like reinforces this idea of being a pattern, what's important here is that you're describing different aspects of your distributions. So first moment is basically related to your mean. Then you have the variability, okay? But all that is symmetrical. You can see here that by calculating this, you can come up with a number that relates to how asymmetrical it is. So if it's skewed, so this third moment is called the skewness, okay, well, or the symmetry. So if it's skewed on one side, here you see it's skewed on this side, this number is going to be below 0. If it's symmetrical and you have a skewness of 0, so that would be your normal distribution, or any like really symmetrical distribution will have this skewness of 0. And skewed the other way, it's above 0. The fourth moment is called kurtosis. That's an ugly word, or let's say a word we're not used to. You could come up with an equivalent that sounds more like common language. The peakedness, so how peaky, how much of a peak it is, okay? So here you have a distribution that's more flat, and you have a kurtosis below 0. Here, something that looks like your normal distribution will have a kurtosis of 0. And if you have something that has that's very peaky, that has a sharp peak, if you want, you have a kurtosis above 1, okay? So remember what those third and fourth moment relate to. Okay, a few more terms here, and that a lot of it is going to be pretty obvious and pretty simple. We saw the mean, the variance, standard deviation, skewness, and kurtosis. The median is a value you probably heard of, and for a normal distribution, your median is going to be very close or identical to the mean. But if your distribution is not symmetrical, or not normal, not Gaussian, you will have a difference between the two. And an example we often think of is that the median for the average and the median salary of people in a certain country, they will be very different because you often have a tale of individuals that are multimillionaires and they pull that mean up, but very, very few people are in that range there. And so the median income is going to be very different from your mean income. So the median specifically is the value where half your samples are below and half your samples are above. So going back to the example of the income, the median income would be the income for which half the people in your population have an income smaller and half the population have an income larger. The mode is something a little bit odd in a way, in that it's basically the most common value in your samples. Okay, and it's not very often used in things that in values that are very variable because you often don't have several values that are exactly the same. But the term is also used in more casually in describing a peak of a distribution, whereas your mode is basically where the highest bar, the highest category will be. And in that sense, it can be useful. We'll see a little bit later this module that we talk about multimodal distribution, and so it relates to this idea of the most common value. Doesn't have to, in a Gaussian distribution, you might have the mode that's very well aligned with your mean and with your median, but in other types of distributions, you might have a very big difference. Okay, the range, so that's fairly easy. It's the difference between the smallest and largest point, largest sample. Percentile, so this is often used, you will see a person or a sample is in the 10th percentile. So here I have an interrogation point. Let's say I'm using the 10th percentile. We often use it, for example, for height. As kids grow, you're like, oh, the height of your son is in the 10th percentile. That means that only 10% of kids in that case have a height higher than, or that their height is higher than your sample. So in that case, your kid. And 90% are below. If you're in the 10th percentile or the 20th percentile, that's the opposite. You have 80% or 90% that are taller and only 10 or 20% that are below. This interquartile range is something actually that relates to the percentile because we use the 25th and 75th percentile as a standard way to show sort of the bulk of your distribution, and you often see this range shown in box plots. So the box plot might show the average, and the box itself is the 25th and 75th percentile, and then you might have bars that extend above that show the variance or the range or something like that. It depends on exactly what they plot in the box plot, but that's often used there. Coefficient of variation. That's something that's useful, and it's particularly useful to compare population, or to compare things that are not in the same order, size order, or in the same range. Let's say you're looking at height and you're comparing elephants and mice. Obviously, if you take only raw numbers, the variability is going to be higher for elephants, because an elephant might vary in height from, I don't know, 2 meters to 4 meters, whereas a mouse is never going to vary by more than a few centimeters. So if you want to sort of bring everything to the same scale, you can do the ratio of your variance over your mean. And so you basically look at your variance normalized by your mean, and then you get this coefficient of variation that you can sort of compare across things that might not be similar otherwise. Confidence limit, we're obviously going to talk about things that are related when we do probabilities and things like that. But the general concept here is that it's the range around a value that indicates how far your estimate is from the real value. And it relates here to the standard error, except that this confidence limit here, you can set your how far your confidence is, and you can say, I want a confidence limit of 95% around my value, and so you can calculate things like that. The standard error, I'm saying it's related to the confidence limit because it helps you to figure out how accurate your estimate of the mean is. So if you have a standard error around the mean, it will help you understand how accurate your estimate is. And how accurate it is will depend on the sample size. So it's related to two things, your sample size and your variance, your variability. Specifically, actually, it is the standard deviation divided by the square root of your sample size. So you take your standard deviation, and the more numbers you have, the more you divide that number. And so if you have a huge amount of samples, your estimate of the mean is going to be pretty reliable. So you'll have very small standard error around your mean. Your standard deviation is not dependent on the number of samples you have, not very much at least. It's simply how variable your population is. So make sure you understand that the standard deviation and standard errors are, even though they're mathematically related, just this divided by n, or square root of n, really makes the interpretation of these numbers very different. So for the standard deviation, it shows the variability in the population. For the standard errors, it shows you the accuracy of your estimate of the mean. Okay, make sure you look at this concept map, fairly simple concepts here, and let's see each other for the next video.